Hi everyone. In today's lesson, we're going to talk about a concept called the extreme value theorem, extrema, and critical values. So first, let's start with the definition of what a critical value is. F of x, the original function, has a critical point at some value x equals c if f of c exists and if either of the following are true. So again, we have a critical value of f of x if f prime, the derivative, is equal to 0, and f prime, the derivative of c, does not exist. So the derivative at c equaling 0 means we're looking for a slope of a tangent line to equal 0. And f prime of c does not exist means where the function doesn't exist, where it has a discontinuity, a corner, a cusp, or a vertical tangent, right? Where I can't take the derivative. So these are really the two things that we're looking for when we're looking for critical values. So let's look at the first one, slope of a tangent line equaling 0. So let's look at this graph here. I want to label all of the critical values. So if you were to draw a tangent line, say here, anywhere here, it's a positive tangent line. Here we have a negative tangent line, but at B we have a specific tangent line, and that tangent line is going to be 0. So here f prime, the derivative, is 0. Tangent line has a slope of 0. So B is your first critical value. Where else do we have that? Well, we have that here down at E. We can say f prime of x equals 0, right? The derivative is 0 here. Almost even down here too at C. So f prime of x equals 0, right? These are our tangent lines. Our tangent lines have a slope of 0. So that's where our derivative would be 0. There's also a second spot of a critical value where f prime of c does not exist. So where does the derivative not exist? Well, it doesn't exist when I have a discontinuity, a corner, or a cusp. So I see here that I actually have a cusp, a straight line into a curve, right? That's my cusp right there. So this value, d, is where f prime of x does not exist. Right? There is no derivative there. So all of these values will be critical values. So we have a critical value at B, C, and E, and those are critical values because that's where the slope f prime of x is equal to 0. And then we have another critical value at D, and that's where the derivative does not exist. And there's no other spots. Those are just critical values. So how can we find a critical value algebraically? So algebraically, what you want to do is you want to do what you see here. You want to take the derivative and set it equal to 0. So anytime a question asks you to algebraically find a critical value, you are taking the first derivative, f prime of x, and equaling it to 0. So let's do that first with this example here. So f prime of x, we'll take the derivative with a simple power rule. 3 times 1/3 gives me 1. Decrease the power by 1. The derivative of negative 9x is just negative 9. We're going to set that equal to 0. And we can factor by dots. So my two critical values will be negative 3 and positive 3. That's it. Okay, how could this get harder? I'm sure you're thinking. Let's look at the second example. So I want to take the derivative again and set it equal to 0. But as at first glance, this kind of looks like a quotient rule because I have a fraction. So I'm just going to make this a little bit easier for myself. I'm going to rewrite the bottom to the 1/2 power, right? That's what a square root does. And then I'm going to bring it upstairs by making the exponent negative. Okay, so now I really have this as my function, and I want to take the derivative. So let's call this f prime of x. So in here, we're going to do a nice chain rule. We're going to take the negative 1/2, bring it in front, keep the base, so keep the 4 minus x squared, and then we're going to decrease this power by 1. So negative 1/2 minus 2/2 is negative 3/2. And in true chain rule fashion, we must always take the derivative of the inside. The derivative of a constant is nothing, and the derivative of negative x squared is just negative 2x. So to clean this up a little bit, because we know we have to set the derivative equal to 0, we actually can multiply or cancel this bottom 2 with this top 2. This negative times a negative is going to cancel. So we really have just this x left times 4 minus x squared to the negative 3 halves. Okay, so to solve this, it's a little different than this basic, do a t-chart, life is good here. We're still going to do the same thing. We're going to kind of do a little bit of a t-chart. And we're going to say, okay, x equals 0 makes sense. And then we're going to set this whole thing at 4 minus x squared to the negative 3 halves equal to 0. And kind of just solve this mini equation. Now, you kind of have to remember that you could raise both sides to the reciprocal power. And when you do that, it cancels the power. So you just are left with 4 minus x squared, and then 0 to any power is still 0. And we can just solve this by dots. Since the 4 comes first, the 2 will come first. So 2 plus x and 2 minus x equals 0. So here x is negative 2, and here x is positive 2. So in this particular problem, there are 3 values of critical points. Okay, so I'm going to leave you guys to try examples 5 and 6 for homework. So again, they're just asking you to find the critical values. It might be a little bit difficult to find the derivatives here because it looks like in both of these, you might need to use a product rule. So do the best you can, and we'll go over those tomorrow. Okay, let's talk about the next concept, extreme values. Extreme values are maximum and minimum values of a function. The extreme points of a continuous function only occur at critical points and endpoints. So there's 2 types of extreme values. You can have an absolute or global extrema, and those are the absolute highest or absolute lowest values. And then you can have a relative or local extrema, and those are any max and min values that are not absolute. So let's look at an example. Let's label all of the extreme values on the graphs below. So it doesn't matter that this one's a piecewise, we're still going to be able to do it. Let's locate the absolute highest and absolute lowest values. And when I say values, we're talking about y values. What is the absolute lowest value for y and what is the absolute highest? So as you can see here, this is the lowest value. There's nothing else lower than it. So this value right here is your absolute minimum. It's the lowest value possible. This guy up here is your absolute max. That's your highest value. And then any local extrema are any maxes and mins that are not absolute. So anything that looks like a maximum would be something like that, right? There's your maximum. Anything that looks like this would be your minimum. So there's a couple of clear ones here. This one is clearly relative. We call it relative when it's not the absolute. So relative minimum, right? It goes down and around like that, right? Relative min. So we have to look for any relative max. Now at first glance, you might be thinking that this is a relative max because it looks like this. However, if it's not an actual point, it can't be a y value, right? We're looking for a possible y value. If this was a closed circle, then you could say it was an absolute max. Now, what about these values? They're a little bit more tricky, but we have to understand where this relative minimum came from. This value is smaller than the rest of the function. See, the rest of the function is above that point. So in this one, is the rest of the function above it? Well, to the left side it is, to the right side it is. How about this point? This point to the left side is above, and this is above. So technically, these are both relative mins because the entire function above it is completely above. Now, this one, on the other hand, is a relative max. And the reason why this is a relative max is because the function is beneath it, right? It's really easy to see when it looks like this or like this, but in these values, it's very difficult to determine. And over here, not a relative max or min because it's an open circle. Okay? So what I would love for you guys to do for homework is try this one. Try to see if you can label all the parts of the extreme values. Okay, last concept is how we apply all of these things to what we call the extreme value theorem. It says a continuous function f of x on a closed interval from a to b attains both an absolute maximum and an absolute minimum. So here, f of c is bigger than any value on f of x. Here, f of c is less than any value on f of x for all x. So simplified, every continuous function on a closed interval will have a highest value and a lowest value. So you see here, this is the lowest y value. This would be your absolute minimum. These values would be your absolute maximum. There would be two of them. So how is this going to ask in a question, right? So here's an AP Classroom multiple choice. Which of the following functions of x is guaranteed by the extreme value theorem to have an absolute maximum on the interval from 0 to 2 pi? So in order to answer this one, we really have to look at the definition. It says a continuous function, f of x, on a closed interval. So they give us a closed interval. So if you can figure out which one of these four answer choices is continuous, then you're likely to have the extreme value theorem guarantee your absolute maximum or even absolute minimum. So I'd actually like you guys to try this one also for homework. I'd like you to try to see if you could figure out which one of these four functions is continuous over the interval from 0 to 2 pi. Once you do that, you'll be able to figure out which one is guaranteed by the extreme value theorem. All right, well, that's it for today. You got some homework to do, and we will touch base tomorrow. Have a good night.